About lines tangent to a circle. Here we have a circle, and within this circle we see some of the main vocabulary terms we've been looking at. We have a chord, we have a radius, a diameter, a secant line, and we also have a tangent line. This lesson is about tangent lines to a circle, and a tangent line is a line that connects to a circle at one point only. Let's take a look. You added this vocabulary last time to your study guide, and let's look here on tangent to remind ourselves what it is. Again, a tangent to a circle is any line which touches the circle in exactly one point. So here we have a circle, here we have a tangent. It has only one point of contact. That's a tangent line. Okay, so we're going to add two new theorems today. We're continuing our journey through many theorems. Just a reminder, a theorem is a statement which has been proven true by a special kind of logical argument called a rigorous proof. So the two theorems we've seen so far are Thales' theorem, the one about a semicircle and the angle within that semicircle that opens onto the diameter. And we've seen theorem 2, the chord theorem, the one where we have a chord and the radius perpendicular to that chord. Let's look at both in GeoGebra just to remind ourselves what these are, because as we start to pile up more and more theorems, it's good to go back sometimes and remind ourselves of the ones we know. So when I go in GeoGebra, this is the first one we learned. Here's Thales' theorem. Again, we have an angle inscribed in a half circle, a semicircle. The thing about this theorem, or the thing that this theorem tells us, is that no matter where we move that angle to, as long as the angle opens onto the diameter of the circle, the angle that's formed here is going to be 90 degrees. Notice this is always 90 degrees. Great. The second theorem we learned is this one. Again, we have a chord and we have the radius perpendicular right here to the chord. It's perpendicular. I really should show the 90-degree angle, but we don't see it. Anyway, this is 90 degrees. But when we have a perpendicular to a chord from the center, the chord is bisected or cut in half. And we can see here the length of CD is the same as length of BD. So now let's move this point. Ooh, no matter how I move that around, no matter what I do to my chord, as long as we have a perpendicular line through the center hitting that chord, it always bisects it. See, you can see it always cuts the chord in half. So that was our second theorem. Today we're going to look at two new theorems. Let's get into it. Okay, so back here again, just to recap again, in Thales' theorem, this angle here, 90 degrees. And in the chord theorem, AM equals BM. This portion of the chord is equal to this portion because this has bisected it. So M is also the midpoint of this chord. Fantastic. Here's theorem 3. And as we've done before, I'm going to ask you first, look at the diagram and what do you see? And now I've added this statement, make a conjecture. A conjecture is kind of like a theory, an unproven theory, a theory based on observation. So what do you see here? What is your conjecture? What do you think is, what can we prove here? What theorem can we pull out of this? Okay, let's investigate. What we have is a radius and we have a tangent line, and we're trying to make some conclusion or conjecture. Let's jump into GeoGebra again, and not just that, I'm going to ask you to open your study guide again, because remember, when we make things in GeoGebra, we then cut the images and put them into our study guide. So open the study guide and then join me in GeoGebra. Okay, so here I am in GeoGebra, and I'm trying to create a situation where we have a circle. Let's look back on it just to remind ourselves. We need a circle, a radius, and a tangent line. Circle, a radius, and a tangent, and then we'll see if we can make a conjecture. Let's try it. Let's get into GeoGebra. So here I am in GeoGebra. I've selected geometry here because we're doing constructions. I'm going to select the circle tool. So here is my circle. I need this circle to have a radius and a tangent. So let's do that. Let's begin with the tangent line. To do a tangent, we see here, construct tangent. We always have to select the point and then the circle that we want the tangent to. So I'm going to hit that point, hit the circle, and I made a tangent to this circle at that point. So now we have a tangent line. You can see it connects this circle only at point B. Now I'm going to make a radius from A to B using the segment tool. So go from here to here. Now we have a radius. Now the radius and the tangent connect here. But is there something special about their connection? I'm going to go to Move tool. I'm going to spin this around Okay, go around to this side. Do they connect in some special way, the radius and the tangent? Well, I hope your brain is saying, I think so. It definitely looks like a 90-degree angle, right? Let's confirm, because it certainly looks like one. I'm going to go to measure, angle. I'm going to select, I need another point on here, so let me add a point first. You need 3 points to measure an angle A, B, and I'm going to put a point C right here. So I use the point tool, and I put a point here. Now back to angle, I'm going to measure it. Angle A, B, C. Oh, I measured the outer one, so let me go back and do the other way. Angle A. Oh, let me do that the other way. 1 second. I need another point. So add another point on this side, right there. Let me see if I go this direction, if it gets me right here. Angle A, B, D this time. Okay, great. It did measure that angle there. The angle is kind of hidden away back there, so let me go to move. Let me grab that label for the angle. There it is. You can see angle alpha, in this case 90 degrees, and we can see the box here for 90 degrees. So that angle at that tangent and the radius is 90 degrees. I'm going to use move and move this around and just confirm the angle no matter what I do. Oh, always 90 degrees. Pretty simple theorem. Looks obvious when you can see it with your eyes, but it's good to confirm it here. 90 degrees right there. Perfect. So you're going to take a screenshot of this and you're going to add it to your study guide by theorem 3. So let me jump. You've discovered that we have a radius and a tangent and they meet at a 90-degree angle no matter what. Perfect. Now don't forget to save using the 3 bars here, put in save and save it as theorem 3, radius and a tangent. Now I'm going to go back to the presentation now. You need to also now go to your study guide and add that theorem. So this is theorem 3. It is your radius tangent theorem, and it says the tangent to a circle is perpendicular to the radius at the point of contact. Okay, so add that and add your GeoGebra image. Paste it in there, your GeoGebra image. Okay. So your study guide is growing. Okay, there it is. There's an image pasted in there. Let's go to theorem 4 now. So same process. We see a circle. Now I see 2 tangents to the circle, but those 2 tangents meet at 1 point. Again, what do you see? What conjecture do you think you can make? What conclusion can you make based on your observation? All right, let's go create this in GeoGebra and see if we can make that conclusion there as well. So I'm going to hop into a new window here. Here we go. I'm going to do a circle to begin. So here's my new circle. I need to create a point outside the circle, so I'm going to use point. I'm just going to put a point out here. There it is. And now I'm going to go to tangents again, right here, tangents. Watch what happens when I select this point and the circle. Oh wow, it created both tangents at once. Because when I said I want to make a tangent and I selected a point and the circle, it was saying I need to construct the tangent from the point to the circle. And there's actually 2 tangents, so we created both of them for us. It didn't know which one we want, so it created both. Perfect. So now we have the situation. Now what do you see? What's this conjecture we can make? And I'll give you a hint. It's something to do with the lengths of segments. What do you think? This might make it easier to see. I'm going to choose the point tool. I'm going to add the point of tangency here in this one as well. Now, when you look at these distances, I hope you were thinking that this segment here is the same length as this one. And that might be what this theorem is about. Let's check it out. Let's measure the distance. I'm going to hit distance here and measure. D to C is given there, and then E to C. Oh wow, look at that. Same length. I'm going to use the move tool, move these labels a little bit. And now I'm going to keep on the move tool here and move C a little bit. Change it around, move the tangent lines a little bit and see what happens to the length of those segments. No matter where I move this point to, notice the segments created between this external point and the points of tangency. Those segments remain the same length no matter what. Perfect, so hit save on that one as well. Save, call this theorem 4, tangents from an external point. So name that there, save it, and then do a screenshot. You're going to add it also to your study guide. So let's go to study guide now. Here we are back in the presentation. You are going to your study guide and you're adding this tangents from an external point. Tangents from an external point are equal in length, and you can see it here. AP is equal to BP. These are tangents from an external point. Awesome. And then you are adding the image you have clipped from your GeoGebra work, put it in there now. Great, so your study guide continues to grow. Now let's apply these two theorems. So grab your notebook, we're going to take some notes or do some practice problems together. First one, read this situation here and see if you can draw a diagram to match that situation. Here's a good diagram for that. We can see a circle with radius 5 and then meeting at this point of tangency, and then it says that to this other point is 12 centimeters. Basically created this situation here, and you can already see the right angle mark there, but when it comes time to do our proof, we should write that first. So angle OTM is 90 degrees. How do we know? Well, the radius tangent theorem, the one we learned about when a radius and tangent intersect or meets, they meet at a 90-degree angle perpendicular right here. Great, now that we've established that we have a right triangle. Since we have a right triangle, we can definitely use Pythagorean theorem, and this question is asking us to find the distance from M to the center. So we're looking for this hypotenuse of this right triangle. So here's a Pythagorean theorem, and I put here Pythagoras, right? We can write this statement because of the Pythagorean theorem. Solving that, OM is the hypotenuse, so OM squared equals the other two sides squared, the sum of those. Putting in the numbers we know, 5 and 12 for these two sides, these two legs. Solving that, on and on, taking the square root, 13. So we can answer the question, the distance from M to the center is 13 centimeters. Great, make sure you pause and take the notes and consider that carefully, but it's not such a tough problem, right? Let's move on. Here's another diagram. Here we are told that x, y, and yz, x, y, yz are tangents from point Y. So now we have this external point and two tangents. Creates this triangle here, and it's asking us to find A and B, these two angle measures basically. So now the second theorem we learned today is about two tangents from an external point. And what did it tell us? Well, it told us that these two segments are equal. So that's why I wrote xy equals zy. And the reason for that, how do we know that? The tangents from an external point. That's the theorem we learned. Tangents from an external point are congruent like that. All right, now that we know that, this is a special kind of triangle. If it has two sides that are the same, what kind of triangle is it? It's isosceles, all right. And when we have an isosceles triangle, it has two congruent angles also. So actually angle YXZ, which is this one, and angle YZX, which is this one, those angles are equal. And how do we know? Because base angles of an isosceles triangle are always equal, okay? When we have an isosceles triangle and we have two sides that are the same length, the angles below those two congruent sides are also equal. So those angles are equal. Therefore, we can write this algebraic statement, this 2a, and I wrote 2a because if these are equal, then we can call this a also. So 2a plus 70 equals 180. Why? Because angles in a triangle always make 180. And finally, this allows me to solve. If I move the 70 here, I get 110. Divided by 2 is 55. So a and b must both be 55. Perfect. Pause if you need to. Consider that carefully. And let's try a couple more. So here's two more for you to try. Here we have this situation. We need the length xy. So we need to find this. Okay, in this one, you might be seeing, again, a right angle here. Because, first, check this out. We didn't have this full length. We only had 8 here. But we have a radius of 5 here. And this is also a radius of 5. These are both radii. So this must be 5. So this helps us get the full length of cy. Now we know CXY, this angle here is 90 because of, again, the radius and tangent theorem, right? The radius meets the tangent at a 90-degree angle. Now that we know this is the right triangle, we can solve for xy. Try it. Okay, let's check our work. 5 squared, which is this side, plus xy squared equals 13 here, the hypotenuse squared. We know that because of Pythagoras. Continue that work, and you can solve for xy equals 12. It's 169 here minus 25, and you take a square root. There it is. All right, check your work again. And let's look at one last one. This one here. This one has a little more going on. Let's see if we can figure it out. How about you try it first, and then we'll check the answer. You're looking for this angle here. Okay, now that you've tried, let's check it out. CXY, angle CXY, CXY. This angle here is 90. Why? Because of the radius tangent theorem, right? This is radius, this is tangent. We know this angle is 90, but we're also shown this is 30. So if this whole angle is 90 and this is 30, how big is this angle? Well, I'm going to call that angle, I put an A here, so I can call this angle AXC, and that angle is 60. And how did I get that? By doing this 90-degree angle minus this 30. This must be 60. Great, there's that 60. Now, can we continue? Can we get x? Well, we know 60. Do we know anything else? Well, we do. I'm going to call this b here first, this point. And I'm going to say BAX. This angle here is 90. Why? Okay, going back to last class, Thales theorem, right? We see an angle here that sits in a semicircle, or an angle that opens to the diameter. So that angle must be 90. And therefore, x plus 60 plus 90 equals 180. These three angles added up make 180. And that's because of angles in the triangle. And finally, that allows us to solve for x being 30. Again, pause if you need to. That's our last problem here. I hope you're seeing the angles all in action here and you're understanding the steps. We will see you soon where you can practice some more.